In this lecture, we want to talk about measures of dispersion. So in the previous lecture, we talked about measures of central tendency. I'll just put CT for central tendency there. And what measures of central tendency try to do was try to describe what a typical data value is. So measures of dispersion, what we want to look at here is we want to measure the spread of data. And to do that, we're going to introduce three calculations here. The range, which will be very easy, and then we'll introduce this concept of called variance and standard deviation. And these two are tied together. And what I mean by that is you'll see that we use the variance to find the standard deviation. Okay, so measures of central tendency, as I said, look to find the meaning of a typical observation. So now what we want to look at is how dispersed or spread out the data is. That's these measures of dispersion. Okay, and this helps us answer like how typical is typical, and for example, if most observations are close to the mean, then the mean is typical, otherwise it is not. So these measures of dispersion put like a numerical value to the spread of data. That's what dispersion is going to do. So put a numerical value on the spread of data. Okay. All right, and here's why knowing the mean is sometimes not enough. And this is the first data set we'll work with in this section. But suppose you have the following. This is important. 2 samples. Okay, so this is sampled set of data of hourly wages in 2 states. And I just made these numbers up. But these are wages in South Dakota and wages in North Dakota. If you were to calculate the average wage in each of these, you would end up getting the same. In both cases, you would see that the mean was $10 an hour. But if you look here at the wages in South Dakota, it's 5, 7, 11, 12, and 15. Where in North Dakota, they're 9, 950, 10, 950, and 12. So it looks like wages in South Dakota are more spread out. So it's one thing to just say, the data is more spread out. What we want to do in this section here is we want to put a numerical value to that, okay? And so when we introduce these numerical measures for dispersion, what I'm hinting at here is that a larger value means the data is more spread out. Okay, so to do this, we're going to look at the range, variance, and standard deviation. So each of these measures have strengths and weaknesses. I'm going to talk a lot about the strengths and weaknesses of the range and use the simplicity of the range to illustrate why we need to introduce different topics or different measures of dispersion called variance and the standard deviation. Okay, so the range simply tells us the highest value in the data set minus the lowest, so that's easy, okay? It's the highest or max value minus the lowest or min value in a data set. Okay, so if you were to look at the range of each, the range in South Dakota, the high max was $15 an hour, the min was 5, so the range here is 10. The range for North Dakota, well, 12 was the high value, 9 was the low, the range here was just 3. It's very easy to calculate here. So look, going back, we said the data was more spread out in South Dakota. And we're seeing that the South Dakota has a larger range than North Dakota, so this range is telling us the data, at least in terms of the 2 extreme values, is more spread out. Okay, so the range, I'm not going to do many more examples because it's really easy. So that's one of the advantages. It's really easy to calculate. It's really easy to understand. So what are some usage? Where might you see this range? So one use of the range is quality control, where absolute minimum may be needed to set for safety standards. For example, suppose you have engineers testing how long it takes airbags to inflate. If they test the airbags and they see that some airbags take 0.7, 0.8, 0.85, 0.95, 0.8 seconds to inflate. If you look at the range here, the high value minus the low value here is 1/4 of a second. And if you've ever been in a car crash where an airbag inflates, 1/4 of a second can mean the difference between life and death. So here what you want to do is you want to decrease that range. Okay, here's the big problem with the range. That's why it's not generally used as a measure of dispersion in the real world. All right, so huge data sets include outliers, and we're going to talk a lot about outliers in one of the next lectures when we talk about box plots. These are observations that are unusual and extreme in value. So for example, if you take a data set of the income of all U.S. workers, okay, the top earner might be somebody like Bill Gates. The bottom income earner might be a street vendor making $1 an hour. You know, if you want to measure the dispersion of typical incomes in the United States, right, like this range doesn't do it, okay? Like this range here is such a large number, it's meaningless. So in this case, range is too large to be meaningful. Okay. All right, so to fix this, we introduce a new measure of dispersion, first called the variance. And so measures of dispersion are meant to describe how spread out data are. So what the variance is based on the deviation about the mean. So what this looks at is how far data values are from the mean. Okay, so how far are data values from the average of that data set? Okay, so to find this deviation from the mean, we look at the difference of data values from the means. And this is where it gets important with notation. So just like population and sample means, we have population and sample variances. So there's two different notations for this, and that's incredibly important. All right, so first off, we have a population variance. So this is a parameter, remember. And we have the sample variance, which is a statistic. All right, the population variance gets the notation sigma squared. Okay, so that's the Greek letter sigma. All right, and the sample variance is literally just s squared. Okay, so we use s to denote the sample variance. All right, so here's what you do. So looking back, I said it's about the deviation from the mean. So what you do is you take the first x value and you subtract away the mean. So remember, mu is the population mean. And then you square it right here. All right, I'll talk about why you square in a second. Then you take the next one. You take the second value in the data set. You subtract away the mean, so you find its deviation from the mean. Then you square it. And you keep going until you get to the last value in the data set. You subtract away the mean, and you square it. And then you divide by how many there are, n. So this right here is the sum of all the x values minus the mean squared divided by how many there are. So really what the variance is telling us is it's telling us the average deviation squared from the mean. Okay, so we're going to undo the square in a little bit. The sample variance, then, it's the same procedure. You have x1, and then you subtract away, instead of the population mean, because it's a sample here, we subtract away the sample mean. And you keep doing that. You square it, and then you go to the second one, you subtract away the mean, you square it, all the way to x sub n, lowercase n here, because it's a sample, minus the sample mean squared. Okay, but then the big difference here is you notice you divide by n minus 1. Okay, in statistics, this denominator is what's called a degree of freedom. And we're going to talk more about that in the when we talk about something called the t-distribution. But for now, just the reason we divide by n minus 1 is when you take a sample, you're likely to underestimate the real variance, and because you're unlikely to sample outliers or extreme values. So to correct for this, to correct that your values, your deviations here are unlikely to be as big as the sum is unlikely to be as big as it should be. They divide just by n minus 1. All right, so again, it's the sum of each x value minus the mean squared. But this time, just remember, sample variance, you just divide by n minus 1 instead of n. Okay, so why square? Okay, so squaring each difference makes them all positive. That's what we want, okay, because if you were to not square them, you'd have some positive, some negative numbers. You'd actually, the sum in the numerator, if you didn't square it, would actually be 0, so that doesn't tell us anything. All right, but squaring makes the final answer really big, so unsquaring the variance, so taking the square root of the variance makes what we call the standard deviation a more useful number. Okay, so now we're going to introduce what's called the standard deviation of a data set. Okay, and we have what's called the population standard deviation, which is just denoted as sigma, right, because you're taking the square root of sigma squared. And the sample standard deviation is just denoted S, and it's the square root of S squared. And these formulas look crazy, but really all it is, the standard deviation, is equal to the square root of the variance. So all you did was square root the variance, and you have this standard deviation, okay? And that's it. So the big thing to remember here is whenever you see sigma, that's a population standard deviation. Whenever you see S, that's a sample standard deviation. Okay, so let's go through this. Let's do this by hand. Let's find the variance and standard deviation for the wages in North Dakota and South Dakota. Okay, so remember, the variance and standard deviation describe the dispersion, okay, which is the spread of the data. Okay, so a larger value means the data is more spread out. So if you look here, all the way back, in South Dakota, the data is more spread out than in North Dakota. So what we should see when we do this is South Dakota should have a larger variance and standard deviation. Okay, when we do this by hand. Okay, so let's do the variance. Let's do South Dakota first. Okay, and remember the formula for the variance, you have to find the variance first. S squared, it's the summation of each x value minus the mean squared divided by n minus 1. Well, recall x bar was equal to 10. So the way I do this, if I'm going to do this by hand, is I use a table to help me out here. So I set up a table. And the first thing I label is my x sub I values. Well, the wages were 5, 7, 11, 12, and 15. Well, look at the formula. The first thing we do is x sub I minus x bar. So this would be 5 minus 10 gets me minus 5. 7 minus 10 gets me minus 3. 11 minus 10 gets me positive 1. 12 minus 10 gets me 2. And 15 minus 10 gets me 5. And look, this is why we square. If you were to take minus 5 plus minus 3 plus 1 plus 2 plus 5, you would get 0. Okay, so that's why up here what it says next is to square it. So this becomes minus 5 squared gets you 25. Minus 3 squared gets me 9. 1 squared gets me 1. 2 squared gets me 4. And 5 squared gets me 25. All right, if you were to sum this up, okay, this would end up getting you 64. So look, my s squared now becomes the sum of x sub I minus x bar squared, which is 64, divided by n is the sample size, 1, 2, 3, 4, 5. 5 minus 1, so this is 64 divided by 4. That's my variance, okay? So the sample variance here for South Dakota is 16. Well, then what is the standard deviation? Well, that's just s, which is the square root of s squared, which is the square root of 16, which is 4. So here we see the sample standard deviation is 4. Okay, so now let's do it for North Dakota. Same deal. Okay. Again, you have to find the variance first. So it was the sum of each x value minus the mean squared divided by n minus 1. And recall again, that x bar was 10. So using that trick of a table, so the values in North Dakota were 9, 950, 10, 950, and 12. So again, you're going to do x sub I minus x bar. So you're going to take each x value minus the mean. So 9 minus 10 gets me minus 1. 950 minus 10 gets me minus 0.50. 10 minus 10 gets me 0. Awesome. 950 minus 10 gets me minus 0.50. And then 12 minus 10 gets me 2. And again, if you were to sum these up, you'd get 0. So let's square them. So you get minus 1 squared gets me 1. Minus 0.50 squared gets me 0.25. 0 squared gets me 0. Minus 0.50 squared gets me 0.25. And 2 squared gets me 4. If you were to sum these up, you get 5.50. So the variance here, s squared, would be 5.50 over 5 minus 1, because there's 5 as well. So this is 5.50 divided by 4. Gets me, plug that in your calculator, you get 1.375. So that's the variance. So the standard deviation, s, is the square root of that, square root of 1.375, which I believe gets you roughly 1.17. Okay, now don't worry. I know I went through this really fast by hand. I'm actually going to show you in a later lecture how to do this in your calculator, and it'll actually be very, very easy. So just notice that, doing it by hand is, I know how to do it now. I know what the formula is. That's great. But in the real world and going forward in the in class, we're going to use technology to help us find these values. Okay. Anyways, I just want to do a second one here. Just kind of showing you the spread of data here. So if you have two different data sets here, it doesn't matter what they're for. But if you look here, data set 1 and data set 2, they both have the same mean. Okay, but what we see here is data set 2 is more spread out. Okay, if you were to go through and look at the values, they're just more spread out. And you see the standard deviation here is almost twice as much. So just so you can see the data more spread out, if you look at the dot plots here, okay, data set 1, values are close together, or closer to the mean, okay? But if you look at data set 2, the dot plot of that, values are more spread out from the mean. Okay, and then that's okay. It just, when the data set's more spread out, just going to have a higher standard deviation. All right, so, what we've seen so far is that larger standard deviation means the data is more spread out. But, is there any application to this? Like, what does it mean to have a standard deviation of 1.17? What about a standard deviation of 4? Do these numbers actually mean anything? Are they useful for anything? And they are for what's called the empirical rule. Okay, and the empirical rule, you're going to see in a second, works for bell-shaped data. So for any quantitative data set with roughly a bell-shaped distribution, okay, so roughly or approximately a normal distribution, the following property holds, all right? Approximately, and this will always hold, okay? This is what the empirical rule tells us. 68% of observations lie within one standard deviation on either side of the mean. So that means from x bar minus the standard deviation to x bar plus the standard deviation, you're going to get 68% of observations. Approximately 95% of observations lie within two standard deviations to either side of the mean. Okay, that is from x bar minus 2 standard deviations to x bar plus 2 standard deviations. You can go out a third one here. Okay, approximately 99.7 percent of observations lie within 3 standard deviations of the mean on either side. So x bar minus 3 standard deviations to x bar plus 3 standard deviations. And you can see this, all right, in the next figure here, okay? Here's a bell curve. Here's the mean. Okay, if you subtract a standard deviation and you add a standard deviation, from here to here is 68% of the data should fall. If you go another out further, okay, add another standard deviation, subtract another standard deviation, from here to here should be 95% of data. And then if you go out to 3 standard deviations away from the mean on either side, it's 99.7% of observations. All right, and you can see this here with the example with North Dakota, just to put some numbers to it. The mean was 10, the standard deviation was 1.17. So what you're seeing here is if you take the mean and you subtract away 1 standard deviation, you get 8.83. If you take the mean and you add 1 standard deviation, you get 11.17. And what we're saying here then is 68% of observations should fall between 8.83 and to 11.17. Just like that. All right, let me give you one more quick example of this, just so you can get an idea of how to use this empirical rule, okay? Let's just suppose heights of adult males follow a bell shape, follow a normal distribution. Okay, so that's the bell shape. All right, with mean, let's say of 5.8 feet. So that's not 5 feet, 8 inches, that's 5.8 feet. And let's just say a standard deviation, let's say of, I don't know, let's say 0.5 feet. All right, what we would then say, all right, or be able to say is 68% of adult males are between, you could take 5.8 and subtract 0.5 feet, and you would take 5.8 and you would add 0.5 feet. Okay, if you were to do that, you would get 6.3 feet, and you would get 5.3 feet. You could go even further. You could say 95% of adult males are between, well, you could go 5.8 minus 2 times the standard deviation, or excuse me, plus the standard deviation, all the way to 5.8 minus 2 times the standard deviation. Well, 2 times that is 1, so that would be 6.8 feet to 4.8 feet. And that's how you would use the empirical rule here. Now, I just made this up just to illustrate the fact, but I hope it helped you see it. All right. Thanks, class.